Inverse variation question. We are going to write the function for the inverse variation. Remember that inverse variation is y equals k over x. It gives us a y and it gives us an x. We're going to use those y and x to find k. We're going to plug in the k, we're going to plug in the x, we're going to plug in the y, and we're going to use them to find k. So y is 3, x is -2. And when we solve for k, we multiply by -2, we get -6 equals k, which means the function is y equals -6 over x. That is your function. And then, part 2, it says find y when x is 4. All you're going to do is just plug in 4 for x. And that's pretty much it. We just have to simplify. We get -3 over 2, or -1.5. Now for number 2, you're just graphing the function that you came up with already. So you're gonna use, if they give you like nice points, you might as well use them. So like for example, these are pretty nice points. You can use -2, 3 as one of your points. If you want, you could use these two, like for -1.5, but you don't have to. There's probably better points we can use. You want to graph your asymptotes first before you do anything. With inverse variation, you're always going to have asymptotes at x equals 0 because you can't divide by 0. So that would create a vertical asymptote at x equals 0. Okay, and you also have a horizontal asymptote at y equals 0. Because technically inverse variations fall under the category of rational functions, and this qualifies as the denominator having a greater degree than the numerator, so bottom heavy. So you have a y equals 0 asymptote. This table is just for you to plug in some more points. You're using this function, so maybe plug in like -3 to go along with this guy, and you'll get 2. And those 2 points will be part of the same curve. So -2, 3, and -3, 2. So those points will be part of this curve. Then you'll need to plug in some points to the right of your vertical asymptote to see what's happening on the right side. With inverse variations, you're always going to have, if half of it's top left, the other half is going to be bottom right. If half of it's bottom left, the other half's going to be top right. That only applies to inverse variation functions. Rational, not so much. So we should expect it somewhere down here. So I'm going to plug in like 1 and 3. So if I plug in 1, I get -6. If I plug in 3, I get -2. Okay, you can plug in whatever you want, but you probably want to plug stuff in that goes into 6, because 6 is k. And there you go. So 2 points per curve. Make sure you label your asymptotes. Questions? Screwed up. Alright, so example 3 is going to be some kind of rational function. I gave this one, but it could literally be any rational function. Okay, so you need to go back and look at all the rational functions and maybe look at more on the internet. Make sure that you're prepared for all of them. If you know the steps and you go through the steps, then you should be able to handle anything. So step 1 is to factor, even if you can take out like a greatest common factor. So for example, we could take out a 2 out of the denominator. So even if you can take out something as simple as a number, like a greatest common factor, and it's just a constant, you want to do that because you never know if it creates a hole. Now in this case, there is no hole because there's no factor in the denominator that's identical to the factor in the numerator.
Is there not going to be a hole in this question because there's no thing that says hole?
Not necessarily. There could have been a hole, I guess. I think just for sake of review sheet I didn't put that, but don't expect that on the test. We'll probably say all the things. But there isn't. So there's no hole. So then when there's no hole, you move on to the next step, which is to find your vertical asymptote. So you set the denominator equal to 0 and solve. So you're setting x minus 3 equal to 0, and that gives you 3. So that's one of your asymptotes. X equals 3. If you look over to number 4, it's the graph of that. So if you want to, like, as you find things, graph them. So I'm going to graph my vertical asymptote. X equals 3, since I found it. What do you mean?
Like this, we took out a 2, do we not set that equal to 0?
Oh, it's just a constant. It's going to go away anyway. Right, so if you have 2, you can divide by 2, and it goes away. It doesn't affect anything. Yeah. Now the other asymptote that you would have, if you have a vertical asymptote, you're either going to have a horizontal asymptote or a slant asymptote. You will have a horizontal asymptote if the degrees are the same or if the degree of the denominator is greater than the degree of the numerator. So in this case, the degrees are the same. Okay? So if the degree of the denominator is the same as the degree of the numerator, then you take the coefficients and divide them. So that would be 4 divided by 2. What's 4 divided by 2? Okay, so you have a horizontal asymptote at y equals 2. If the degree of the numerator is greater, then you do long division and you have a slant asymptote. That's number 12. Okay. The intercepts are points, so find the intercepts and then you can put those in here if you want. So your x-intercept is going to be the x value when y is 0. So you take your function and you plug in 0 for y. First step would be to multiply both sides by 2x minus 6. And so you get 0 equals 4x plus 1 when you do that, because the 0 times anything is 0. Then you can subtract 1 and divide by 4. So you get negative 1/4 equals x. So right here, you're going to write negative 1/4, comma 0. Like I said, if you want to put that here as one of your points, you can. Or you could pick something else if you want. I might as well. It saves you some time and you might need the extra time. So that's going to be like right around here. Your y-intercept is going to be your y value when x is 0. Whoops. So you're going to plug in 0 for x. You're not necessarily guaranteed to have an x-intercept or a y-intercept, so just keep that in mind. You might not have them, or they might be irrational. Right, so this gives me 1 over negative 6, so that's 0 comma negative 1/6, which is like pretty much like right next to this point. Can't even really see it. So I'm not going to necessarily put both of those here. I'm going to put one more point over here so I can get a better look at this graph. So I'm going to try to plug in 2. So I can see like kind of like what the curve looks like. So if I plug in 2, I get 8 plus 1 over 4 minus 6, which is 9 over negative 2. So that's negative 4.5. So 1, 2, 3, 4.5. So that gives me a little bit better of a point to graph so that I can get this curve looking good. But again, you can pick whatever points you want. So this is enough for that left curve. I need something on the right. Now, it could be down here, it could be up here. It's a rational function, so you don't necessarily know. So just, we do a lot where they're like alternating, but it is possible for it to be like this. But this, I don't think, is one of them. So because our asymptote is at 3, we're going to plug in things to the right of 3, so say 4 and 5. So if I plug in 4, I get 16 plus 1, that's 17, and I get 8 minus 6, that's 2. So 17 over 2 is 8.5. It's gross, but it's not that bad actually. At least it's like 8.5 and not 8. And yuck. 17/27. Okay, and then plug in 5. So this part would be the only part that, like, in theory you would want to use a calculator on, but I just don't feel comfortable with the whole calculator thing, because I just feel like you guys are going to depend on it, and that's bad. And you really need to know how to do this without a calculator. Okay, so hopefully you can, like, add and multiply. I get 21/4, which, yeah, so I get 5.25 because it goes in 5 times with 1 remainder. So 5, so something around here. So this guy goes like this. Voila! So pretty. One question where you're not necessarily graphing anything, I'm just going to tell you to find like asymptotes and holes. So you don't have to graph them, you just have to find them. In order to find asymptotes and holes, you have to factor first. If there's a number in front of your x squared, to factor, you usually multiply. So when I do it, I factor by grouping, so I multiply these two together. And then I look at the factors of -3, and I see if any of them add to 1x. And in this case, they don't. Okay, so if this was like a 2x, then I would probably pick these two. But since it's a 1x, none of these factors of -3 add to 1x, which means this doesn't factor. So if this doesn't factor, then that means I don't have any holes, because the numerator and denominator don't have any common factors. Now if you look at B, down here, this may factor. Is there anything that multiplies to 27 and adds to -12? There you go. And so you can see that these two are the same. You'd cancel them and get 1 over x minus 9. If you can cancel something, that makes it a whole. So if we cancel x minus 3, then I have a whole at 3 something. So whatever you cancel, you set that equal to 0 and solve. That gives you the x coordinate of your whole. If you want the y coordinate of your whole, you take the x and you plug it into the simplified version of what you just found. So I plug that back in, I get 1 over -6. That's my y coordinate of my whole. Okay. There's only one way to find that, and it's by plugging it into the simplified version. If you plug it in the original, you're going to get something over 0, like 0 over 0 in this case. That doesn't make sense. Okay. Whenever you want to find where a point is, you plug it into the function. So that's what we did. All right, let's go back up to this one and find asymptotes. So your vertical asymptote, you just set the denominator equal to 0.
Oh dang it, what was the horizontal?
Well, you're going to find all of them. So your vertical asymptote is x equals -2, because when you set x plus 2 equal to 0, you get -2. Right, then you're either going to have a horizontal or a slant asymptote. If the degree of the numerator is greater than the degree of the denominator, you have a slant asymptote. And if you have a slant asymptote, that means you have to do long division. So some long division over here. What do you multiply x by to get 3x squared? Yeah. So I'm going to put that here. After you put it there, you multiply. 3x times x is 3x squared. 3x times 2 is plus 6x. Should have given myself a little bit more room. Okay. Then you subtract everything. So you subtract. X minus 6x is -5x. Then you go, what do you multiply x by to get -5x? -5. And then you can stop. So once you fill this in, we don't care about the remainder. Our slant asymptote is at y equals this guy, 3x minus 5.
Wait, how did the 6 become a negative 6?
Because after you multiply, you subtract everything. So I subtracted x minus 6x. If you have a slant asymptote, you don't have a horizontal asymptote. Now, in B, we had simplified this to 1 over x minus 9. This is what you should be looking at for the remainder of the stuff. Don't go back to this. Okay? So always use the simplified function, not the original function, for finding the asymptotes. So my asymptote, if I set the denominator equal to 0 and solve, is going to be x equals 9 for my vertical asymptote. And then my horizontal asymptote, since the degree of the denominator is greater than the degree of the numerator, is going to be y equals 0. So always, when the degree of the denominator is greater than the degree of the numerator, your asymptote is at y equals 0. So bottom heavy, y equals 0. Top heavy, do long division. If they're the same, you look at the coefficients. So those are my asymptotes, and then I'm supposed to say the domain and the range. It says set builder notation. Okay, so set builders, the squiggly little squiggles. I don't know if I can, so squiggle. I'm going to say x is such that x is not allowed to be 9, because that's my vertical asymptote. Also, hold on, I forgot one. Also, if you have holes, you want to include those as well. So if you don't have holes, you don't have to worry about it. But this one has a hole and a vertical asymptote.
Wait, so which ones do you take for the domain?
So if you have a hole, then that means that your graph doesn't exist at that place. So I'm taking this, taking the x value of my hole and the vertical asymptote, because those are x values that I can't be. And then your range is basically the same thing, but with the y values. Y can't be negative 1/6
Oh my God, I put the 0
or
first.
0. Eh, it's okay. You can fix it.
What are the points off of that? Is it-
I probably wouldn't notice. I don't know.
I put the 0 before the negative.
Hope she doesn't notice.
Now, if you don't have a hole, then all you're putting there is the asymptote. Okay? So, vertical asymptote for x, horizontal asymptote for y.
I keep yawning and I'm actually confused with you wanting
Number 6 has a little bit of a typo. So
did not work.
if you tried it already, yeah. So this is supposed to be a 4. Makes it a little bit
My
nicer.
problem was like 3x
So,
cubed plus 2x
Is 6
squared.
I know.
supposed to be 4?
Change this to a
Oh
4.
my God, do I have to erase the entire thing?
You just do it on the back. Just do it on the back.
Yeah, rewrite it out.
So what we need to do is we need to simplify the numerator. And after we simplify the numerator, we're going to divide by the denominator.
So that's supposed to be a 4.
Yeah, it's supposed to be a 4.
How do you realize that?
Because she's math.
Because the problem did not
It's
work.
not cute anymore when it's not a 4. Like, nothing cancels, right?
Yeah, I literally just had to multiply together and it was like.
That's fine.
cute.
You should never expect, here's the thing, is like, I'm going to make typos sometimes. You have to keep going. Don't expect it to be cute. It could not be cute, and maybe that wasn't my intention, but you have to keep going. And in general, like, just because we want it to be cute doesn't mean that it has to be cute. So you always want to make sure that you keep going, just in case. Proceed. So we need, in order to simplify the numerator, to find a common denominator. So I'm going to multiply this fraction by x plus 2 over x plus 2. And I'm going to multiply this fraction by x minus 2 over x minus 2, so that both fractions have an x plus 2 and an x minus 2 in their denominator. So this is 2 times x plus 2 plus 1 times x minus 2 all over our common denominator.
Number 12 is graphing, and we do not.
Now the whole point of finding a common denominator is so you can add the numerators. So you're going to simplify the numerators and add the two quantities that you get. Now adding is easy, but sometimes subtracting is not easy. So if there's a subtraction sign here, you have to distribute the subtraction sign. So let's pretend this was a subtraction sign. You'd get 2x minus x and 4 minus negative 2. 4 minus negative 2 would have made that 6. Okay, so just keep that in mind. Now, we don't have a subtraction sign, so we get 3x plus 2 up there. This is all divided by the denominator. Okay, so because it's division, we're going to keep, change, flip. So I'm going to flip this upside down. While flipping, I'm going to factor that denominator because it factors to x plus 2, x minus 2. Now that we changed it, at least.
Yeah, the other one was a
And so now the x minus 2's and the x plus 2's cancel, and we just get 3x plus 2 over 6, which you can leave as such. Okay.
Dang, I did all of them to 10. I'm gonna be very bored.
Number 7. 7 is just a basic division question where you're simplifying. So you want to start off by factoring everything. So that first fraction, you can take out a 3 out of that first guy. So sometimes all you can do is just take out a greatest common factor. The denominator factors, it's a difference of squares to x plus 2 and x minus 2. I'm going to keep, change, flip, so I'm going to multiply by the reciprocal of this. So this factored is 4 times x plus 4. That's now on the top because I keep, changed, flipped. And this factored, I can take out a 4x, and I'm left with x plus 3. And it's now in the denominator because I keep, changed, flipped. Okay, stuff that cancels. You can cancel x plus 3. You can cancel this 4. This is an x plus 4. This is an x plus 2, x minus 2. None of that cancels. There's no things that cancel with 3. There's this random x here. So this first fraction is 3 over x plus 2, x minus 2. This second fraction is x plus 4 over x. There's still, again, nothing that cancels. So you're left with all the things just multiplied together. Okay, which all of that simplified is going to be 3x plus 12 over x cubed minus 4x when you multiply it all out. There's a few ways you can solve this. If you want, you can multiply by x minus 2. Or you can change this to negative 6 over 1 and cross multiply. Either way, you get the same result. So 4x plus 2 would be like if you cross multiply, and then x minus 2 times negative 6. Like, it's the exact same thing. Yeah. But
it looks easier when you cross
it looks easier when you cross multiply. That's why I brought it up.
Maybe
So
feel better about it,
yeah.
you know?
So I would need to distribute the negative 6, which would give me negative 6x plus 12. And then, this is easy, this is just linear, so no, you don't even need to do that. So just add 6x, you get 10x plus 2 equals 12, subtract 2, 10x equals 10, and then divide, you get x equals 1. And the last thing you want to do is just check to make sure that your answer isn't extraneous. The only thing that would have been extraneous here, or our only restriction, is that x cannot be negative 2. And we got x is 1. So that's our answer.
You mean x can't be 2?
Oh yeah, sorry. Yeah, 2, not negative 2. 2. Thank you. But we got 1, so we're good. You can also like actually plug it back in. So if you actually plug it back in, you'll see you get 4 plus 2, which is 6, over 1 minus negative 2, which is negative 1, which is indeed negative 6. So you can check your answer and make sure it's correct, like you would for any other equation. All right, so which one of these is harder? They're both about the same.
So the second one has 2 answers.
Yeah, let's do number 10 just in case we don't have time, and then I'll go back and do 9 if we do have time.
But with the answer to 9-1.
What?
With the answer to 9-1.
I don't remember. First thing we would want to do for these rational equations is if you can factor, you want to factor. If you don't have to factor, then don't factor. But for both of these, you would factor. You want to factor so that you can see what the denominators all are. Every denominator needs to be the same. In this situation where you might have 3 different factors, you might have to multiply every fraction by something, okay? This first fraction has a denominator of x plus 3 times x plus 1. This second fraction has the x plus 3. The last fraction has the x plus 1. We want every denominator to have both x plus 1 and x plus 3. So this needs to be multiplied by x plus 1. And this needs to be multiplied by x plus 3. This first fraction doesn't necessarily need anything because it has already the x plus 3 and the x plus 1. So I get x plus 9 over common denominator plus, when you multiply these two together,
You get x squared plus 2x plus 1.
good, so you have to FOIL.
And then you get 2x squared plus 6x.
Yep, here you distribute. Now remember, the whole point of finding a common denominator is so you can add the numerators. So that's what we do. We add these numerators and we get x squared plus 3x plus 10 over our common denominator.
Wouldn't it be 3x squared? Oh, they're equal to each
Oh
other.
yeah, it's equal to. So now, once you have common denominators, you have equal denominators, you can get rid of the denominators. Before you get rid of the denominators, you might just want to make a note of the restrictions. So our restrictions are -3 and -1. So I'm just going to write that at the top. X cannot be -3 or -1 in case I get those as my answers. Then I'm going to ignore the denominators and just solve the numerator equation, which is quadratic, which means get it set equal to 0. So subtract x squared, subtract 3x, and subtract 10. And then for this particular question, you can factor, but you can also choose to use the quadratic formula if you want. This factors to x plus 5, x minus 2, because 5 times -2 is -10. 5 plus -2 is +3. I set those those factors equal to 0, and I get x equals -5 and x equals 2. Are either one of these extraneous? No, because the only values that could have been extraneous would be -3 and -1. So they're not extraneous. You're going to assume they're correct. If you want to assure that they're correct, plug them back in. That's only if you have time, because that's going to take some effort because they're fractions. Okay? Questions? Now, so for you guys, you'll have like a question like number 11 probably in the place of a question like number 9. So instead of having 2 plain rational equations, one of them will be a system. And I think I put like the absolute hardest system on the review sheet, so that like you should be prepared for like anything in theory. So if your system of equations has lots of x's in it, then you want to keep an equation with x's in it. You don't want to try to solve, like, so see how this says x equals y minus 3? We don't necessarily want to plug y minus 3 in for x, because you see how that would take like forever? Yeah, such a hassle. So instead, I'm going to solve this second equation for y. And so now that's going to be a lot easier to take this and plug it in for this y than it would have been the other way around. Because you only have to plug it in once instead of 3 times. So when we plug that in, we get x plus 3 equals x plus 2 over x squared plus 3x plus 2, and then all of that plus 2.
A little plus 2 on it is so obnoxious.
I know, it's obnoxious. I'm going to get rid of it right now. So I'm going to subtract 2 from both sides, and it gets rid of that guy. So that's just kind of combining stuff. Now what we have left, this is a rational function, like the one you just did. So we would probably attempt to find a common denominator, or you could multiply by the denominator if you prefer. I was going to say, or you could attempt to simplify this. So
It goes to x plus 2, x plus 1.
and we did a question like that yesterday where that makes it a lot easier, right? So if you factor this, and so we're left with 1 over x plus 1
And then they kind of
equals x plus 1.
equal each other.
And this is a lot easier to solve. I'm kind of running out of room here.
And then you can just multiply by 1. I think. Or
So, well, so this is like what I have over here is this is like x over 1 plus 1 over 1. So you can't cross multiply because it's not fraction equals fraction. It's fraction plus fraction equals fraction. I think what I would do is I can multiply both sides by x plus 1 like this. And so what happens is on the right side, these would cancel and you'd just get 1. On the left side, you'd FOIL these out and get x squared plus 2x plus 1.
Then just
Subtract 1, you get x squared plus 2x equals 0. And then with that, you just factor out an x. So it's not a trinomial anymore. You just take out a greatest common factor and then set those guys equal to 0.
X equal to -2.
Indeed. There's not enough space here. So, 0 and -2 for x. But remember, it's a system. So for systems, you have to plug them back in and find y. Now, fortunately, we have these two nice simple equations that we can plug x back into. So I'm going to look at this one. If I plug 0 back in here, I get 3. So 0, 3. If I plug -2 back in here, I get 1. So those are my two answers. 0, 3, -2, 1. I should have put one of these on the back.
And none of them are actually. Are any of them considered extraneous?
Extraneous, actually, because I didn't do that. The
-2 is not.
this guy, denominator, would have created extraneous since we factored it over here. -2 and -1. So we did get -2 actually, which means this guy is extraneous.
Can I just if I wrote it like this?
What it means is graphically, what it means is graphically, these two functions are intersecting kind of at that point, but that point is a hole. So it's like this graph, which is a line, is touching this rational graph, but it's touching it at a hole, which is why it's extraneous. So they are intersecting per the eye, but in reality, they can't intersect at a hole because the hole is a point of discontinuity. Okay. So the last one's a graph of, it's got a slant asymptote graph. I hope I have enough space here. I don't think I do, but we'll try it anyway. So any rational function, you always start off with, can I factor? So can you factor?
Yes.
What is a factor to?
I mean, never mind. That was a 4.
Yeah, it doesn't factor. So if it doesn't factor, then we move on to vertical asymptote. So vertical asymptote, you take the denominator, set it equal to 0, and you get
X.
3.
Don't you have to do long division too?
You do.
What did you just do? I wasn't paying attention. I sure.
So we couldn't factor, so we moved on to vertical asymptote. So set denominator equal to 0 and solve. Okay. Now, because it's top heavy, or the degree of the numerator is greater than the denominator, we do long division to find the slant asymptote. I've never written so tiny in my life. Okay. So, what do you multiply x by to get x squared?
X.
And we're going to put that here. After you put that there, you multiply x times this x, and you get x squared. X times negative 3 is negative 3x. After multiplying, you subtract everything. Subtract, and when you subtract a negative, you're really adding. These should cancel, and I get 2x plus 3x is 5x.
X plus 5.
Yep, and then what do you multiply x by to get 5x? 5. So plus 5. Now, we can stop. We don't care about the remainder. Whatever you get up here, that's your slant asymptote. So y equals x plus 5 is the slant asymptote. To graph that, this is a line. It has a y-intercept of 1, 2, 3, 4, 5. Okay, y-intercept of 5. It has a slope of 1. So you're going to go up 1 over 1. And you're going to turn that not into a line, but into a dotted line to make your slant asymptote. Oh my god, there's definitely not enough room here. I hate my life. Did you get the idea?
Wait, what did you do? Go up 5 and then to up 1 over 1?
Yeah.
Oh, is there gonna be one over here? Because it's just not gonna work.
I know, I think there is. I don't know though. Alright, so now I'm not going to force you to find the intercepts. If you want to find the intercepts, you can. If you don't want to find the intercepts, you don't have to, but you need to graph it. So if you want to find the y-intercept, that's super easy. You just plug 0 and 0 and 0, and you get negative 5 over negative 3. So that's 5/3, which is like 1 2/3, right there.
What did you just do?
The y-intercept, if you plug 0 in for x,
Oh,
because it's like the easiest
it goes
point.
to negative 5 over 3, right?
Yeah. So if there's a point here, it does mean that the other points are up there. I know, I'm just as upset about it as you are. So you have to pick x values that kind of fall in between these asymptotes. So if you look, this asymptote is at 3. I don't exactly know where this asymptote is, but I know that like these points are probably within range because I didn't use a ruler, so I'm not totally sure where it goes necessarily, but I do know that it's like in this realm, so I could plug in like 2. So plug in 2 up here,
What do 5/3 equal?
1 2/3.
I had 3 over negative 1.
So 4 plus 4 is 8. Yeah, 3 over negative 1. So that's negative 3. Ooh, that's a good one. So that's right here.
Why did I? Yeah, I went the wrong.
And so usually these things, they look like funky parabolas of some kind. Maybe want to plug in another point to find exactly the shape. Maybe not.
Not feeling it.
And then you would plug in points to the right of 3 to get whatever's happening here. So like 4 and 5, and then it would give you points that are way off my graph, unfortunately. And so, there you go. So that's like your slant asymptote graph.
Ooh, that was so bad.